A good example is traffic on a highway. Every car is driven by a person, and this person is what we call an intelligent agent. They're making decisions which are the best for them based on the information available to them. Every once in a while, things happen which aren't predicted by standard theory. Somebody steps on their brake, and the brake lights cause everybody else to choose to slow down. And so the traffic will be moving along, and there'll be this wave of cars slowing down, which will go and take on a life of its own.
You recognize that a system comprises many interacting entities. Those entities could be molecules, they could be people, they can be animate or inanimate, which are interacting with each other based on local rules of interaction, which may be adaptive and continually changing, but they're not necessarily subject to some kind of global control or direction.
And so a part of what our complex system effort is about is in developing the tools that will allow us to expose that complexity, to understand those feedbacks, to understand those so-called emergent properties.
Lake Champlain is a really unique lake in that if you look at the sort of blue stripe of the lake down the middle of its basin, there's 19 times as much land area as there is water area in the whole Lake Champlain basin. And what that means is that when it rains, 19 times as much rain is falling on the surrounding landscape as is falling directly into the lake. The lake is an absolute wonderful indicator of our behavior overall. The lake reflects the whole watershed that drains down to it.
So it's a very, very complex system, and you can imagine looking at a variety of different aspects of that.
The emergent behavior that we're interested here are these algae blooms. So how do these factors come together? How do they interact to produce the algae bloom? Can we develop computer tools that help us answer some of those questions?
Since the late 90s, about 2000, the blooms have been dominated by what we call cyanobacteria, or blue-green algae. And it's a particular kind of algae that can produce a toxin. And the toxin can make you sick if you ingest too much of it.
So one popular explanation for why the algae blooms are occurring in the lake is the amount of phosphorus in the water. That phosphorus is being washed in from farms around the lake. And phosphorus is probably a big contributing factor, but there are probably tens or even hundreds of other contributing factors that also contribute to it.
Unfortunately, we know that agriculture isn't the whole answer to what's going on. Clearly, agriculture is part of it. We also fertilize our lawns and gardens. Our pets produce waste. But fundamentally, probably the most damaging thing that we've done is change the way our rivers and streams carve their way down to the lake.
Within complex systems, we often talk about intelligent agents, things which are reacting to their local environment without global knowledge. And for example, it could be even something like a rock which is rolling down a stream.
There are interactions, there are feedbacks, there are loops that we don't fully understand.
The way we're going about trying to tackle this complex systems problem is first and foremost to recognize that one person can't do it. We've brought together people who are experts on stream dynamics and on biology of streams. We have brought in people who are computer modelers, and we've brought in people like myself who are familiar with statistics and fairly good at statistics.
We're now speaking the same language, so the computer scientists have a good idea about what the biologists know about the problem and what they don't know. And my contribution to the group is to try and develop computer tools or develop computer programs that can help us understand why these problems are occurring. What are these mathematical building blocks? There are a lot of components and factors to the lake. There's the lake itself, there's the nutrients that are washing into the lakes, the streams and watershed, the people that live around the lake, the weather that passes over the lake. These are all factors that contribute or interact with one another to produce certain emergent behavior. So one of the tools that we're developing as part of this group is an evolutionary algorithm. Some of these mathematical explanations are better at explaining these blooms or predicting why they occur than others. The ones that are good at explaining the blooms are kept, and the ones that aren't are deleted by the algorithm. That better explanation will then eventually replace the older explanation in the population. And if you repeat this process long enough, you eventually achieve an explanation that might combine tens or hundreds of contributing factors.
We try and use principles from biological evolution and apply those to solving problems on the computer. So if you think about it, biology has just done an amazing job of creating optimizations. Animals are evolving continually, generation over generation, in response to different changes in their environment, changes with each other, their interactions. What we try and do is use some of those principles when we're writing computer programs.
The type of modeling that I'm working with is called neural network models or artificial neural networks, which are models that are based on the premise by which we think our brain works and our brain learns. Using part of your data set, you teach the model the patterns that are found in nature. So you train the model on one part of your data and then you test it on something else.
Essentially, it's a form of evolutionary programming that's sort of informed by the way that biological systems work. By mutation and recombination of different components of the model actually creates itself to best fit the data. My role is pretty well defined as the liaison between the biologist and computer scientists. The people here, there are experts in both genetic programming and artificial neural networks and are very strong in what they do, so it's a good experience to see how to apply this modeling technique to environmental problems.
So we have amassed a considerable amount of data on the lake, on land uses within the watershed, on the climate, on urbanization patterns, agricultural patterns.
Now, those data sets have not been collected in a nice, orderly, controlled way. People have used different methods, different sampling times, different locations. So part of our work has been to standardize and organize those data so that they can be in a form that we can apply the complex systems tools to.
So if we can come up with a good explanation, not only for where and when these blooms are going to occur in the lake, but why, we can start to inform policy. We can have a better understanding about what we need to do or what we need not to do to make sure these blooms don't occur.
And so the model that we develop here, of course, will tell us quite a few things about the lake, but it is a general form of analysis that could be applied to other lakes or other kinds of systems.
What I am excited about on this is that there's really is a magic in this world. That the world is not something that we can take it into little parts and understand it and put it back together. And one of the things which I really love about complex systems is that it's really made me appreciate that magic is real. That there really is a part of the world which we are not going to understand by breaking it into little tiny pieces.